In this video, our objective is to find intervals of increasing or decreasing for a function. When we say increasing or decreasing, these are actually properties for a function that apply to a function either entirely or over an interval of its domain. So let's precisely define these two flavors of monotonicity. So this is it's a mouthful, but we often just say that the function is monotone. Monotone meaning that it doesn't change direction, and by that we mean that we have two flavors. So f is monotone increasing, and we'll often just say increasing. We'll stop saying monotone. On an interval a comma b, if for all x sub 1 less than x sub 2, so two numbers in that interval where the first one is smaller than the other one, then we have that the corresponding y values are also ordered in that sense. So if x1 is less than x2, then f of x1 is less than x2. So we can also think of this as y1 is less than y2, right? The y values also have to be ordered in that sense. So we'll see a picture of this in a second. 2, f is monotone decreasing, and again, we'll just say decreasing from here on out, on a possibly different interval. If for all x sub 1 less than x sub 2, so numbers in that interval where one is less than the other, then we have the opposite, which is f of x sub 1 is greater than f of x sub 2. So in this case, the y values, the order of them is switched. So if x1 is less than x2, now y1 is greater than y2. And then one, not boring necessarily, but one trivial case is we say f is constant on that interval if for all x sub 1 not equal to x sub 2, so two different x values in that interval, then f of x1 is equal to f of x sub 2. In other words, the y values always match. So we'll see a few examples now of each of these kinds of properties. And again, this is over a specific interval, so your function may be increasing or decreasing on different intervals, but it is a property that holds on an entire interval, not at a single point. So let's see some examples. So our first example, we're going to consider the function y equals the absolute value of x minus 3 plus 1. And I'm going to graph this function here. So if you need a refresher, remember this is a absolute value style function. And it has a corner at 3, comma 1. So here's 3, comma 1. And then its slope is 1. So it's just a shifted absolute value function. Not a great graph. But where is this function increasing? Well, let's examine the graph of this function. And we say a function is increasing if for any two values in that interval, then the corresponding y values have to be ordered in the same way. So in other words, let's just take the point 3 and the point 4. Okay, so our x values are x sub 1 is 3, x sub 2 is 4. 3 is less than 4. So what we're saying then is, are the y values at 3 and 4 also arranged the same way? So is y1 less than y2? So y1, if you plug in 3, remember that gives us 1. And y2 is 2. So in this case, x sub 1 less than x sub 2 tells us that y sub 1 is less than y sub 2, which means this is increasing at least for an interval that's containing 3 and 4. But now that we understand how this plays out, we know that if we examine every part of the right half of this function, so this entire segment here, well, ray actually, represents the function being an increasing function over that interval. So our answer is we're increasing over the interval to infinity, because we know it goes on forever. We don't have the exact. We don't have the full picture, obviously, because we can't go out to infinity. But this represents the majority of the behavior of this graph. And remember, and notice that we don't include 3 in this interval. So this is only defined for open intervals. We're always going to use open intervals for this. All right, let's see an example now where we're looking at a decreasing function. So consider the function e, a function of r, equal to r to the negative 2, which, if you're not comfortable working with the negative exponents, you can write this as 1 over r squared. Okay, so I'm going to graph this, and you can use Desmos if you'd like to graph any of these functions as you're working through this, but just keep in mind that sometimes we're going to need to rely on the function statement alone and not on not on the graph. So it passes through the point 1, 1 and through the point 2, 1/4. This is the graph of this function. This is r, this is e. And now, importantly, this function is decreasing over the interval 0 to infinity. How do we know this? So as we move from left to right, so here's x1, here's x2, the y values drop. So the corresponding y value here, let me use more color. So this is y1, this is y2. Now 1 is greater than 1/4, so that's why this is flipped. Does that make sense? So if your graph goes down from left to right, it's decreasing. If it's going up from left to right, and the function is increasing. And notice in both cases, these functions that I've selected are not increasing or decreasing on their entire domain. For instance, example 1 is actually decreasing from negative infinity to 3. I'll add that here. And this function is increasing on the interval negative infinity to 0. Notice I haven't included 0 again, in this case for two reasons. The first being that 0 is not in the domain of E, and secondly, we don't include the endpoints ever. All right, so intervals of increasing and decreasing. We often are going to be asked for a given function to express the intervals of increasing and decreasing, which is basically look at all the graph of the function and examine for what intervals it's increasing and what intervals it's decreasing, right? So here's an example. We're going to find intervals of increasing, which I'm going to abbreviate as II, and intervals of decreasing, which I abbreviate as ID, for the function f of x equals x squared times x plus 3. All right, so how do we do this? Well, what are we dealing with here? We have a polynomial function that has zeros and turning points. So if you've ever seen a graph of a polynomial function, you should have, you'll know that it can go up and down a certain number of times, and every time it changes from going up to going down, we call that a turning point. Specifically, if we graph this, let's think about what zeros. So in other words, the y-intercepts. So the x-intercepts. X-intercepts. Well, if you solve this equation, f of x equals 0, then we should be able to figure out what x values give us a 0. So zero factor property tells us that 0 equals x squared or 0 equals x plus 3, which means either x equals 0 or x equals negative 3. All right. Moreover, x equals 0 has multiplicity 2. When we have an even multiplicity, that typically means that we're turning around at that point. So it's also a turning point. Okay. So let's graph this function. And some of these things I already know because I've worked with this function before. But you should graph this on Desmos and verify that these are indeed the points where they turn around. So we know we pass through 0, 0. We know we pass through negative 3, 0. And then by selecting a few other x values to plug in, I find that we also pass through negative 2, 4, and through 1, 4. So ultimately, this function should look like this. Okay, so let's look at this function. We have two turning points. Let me highlight them. Here's one turning point, and here's one turning point. What we say turning point is a point where f changes from increasing to decreasing or from decreasing to increasing, or vice versa. Sorry, I was pronouncing that like Tigger in the Tigger movie. So this tells us that at these points is where we should change up our intervals of increasing, decreasing. So let's examine it from left to right. So on the left side of this first turning point, we're looking at the interval negative infinity to negative 2. And as you're moving from left to right, the function is actually going up. So think of us as a ant. We're an ant crawling alongside the... That's my terrible ant drawing. We're crawling up along the side of the graph of the function. And so from left to right, you're crawling up, which means this is increasing. Then you hit the top of the hill, and now you're decreasing because you're going down. Then you hit the bottom of that hill, and again, you're going up forever. So you had better have packed a snack or two as an ant. All right, so what does this mean? This means our intervals of increasing, we have the interval -infinity to to -2. That's this interval. Union the interval 0 to infinity, which is this part of the graph. The union symbol, by the way, just a refresher, union means or. So we're taking both of these intervals as part of the solution. Now, our intervals of, or in this case, intervals, or interval, because there's just one, of decreasing is where the ant is going down. So that's from -2 to 0. And that's it. That's our answer. All right. So now, here's you try it. So find intervals of increasing and intervals of decreasing for the function y equals 1 over x squared minus 9. All right, so use Desmos if you'd like. Use your skills of plotting rational functions if you'd like. But at the end, you should have two distinct answers, a union or possibly just one interval for each one. So you need the intervals of increasing and the intervals of decreasing.